Okay, this is section 2.4, solving systems using the inverse matrix. First, the definitions. The identity matrix, which we denote with an I or sometimes I sub n, is a square matrix containing ones down the main diagonal and zeros everywhere else. The identity matrix has the property that for any matrix A, the product A times I is just A. Okay, so for example, here we have a matrix I'll call A. It's the matrix with 2, 1, 3, 5 in it. And then here, this is a 2 by 2 identity matrix, which I will denote with I. Okay, it has ones down the main diagonal and zeros everywhere else. So this is the identity matrix. Well, the 2 by 2 identity matrix. There's a identity matrix for every dimension. Okay, now notice if we do this multiplication out, recall how we multiply. I take this row times this column, pairing up numbers. 2 times 1 plus 1 times 0 gives me 2, of course. And then 2, if I pair up the first row with the second column there, I get 2 paired with 0 and 1 paired with 1, so I get a 1. And now if I pair up the second row with the first column, I'm going to get 3 times 1 plus 5 times 0, that's 3. And now if I pair up the second row with the second column, I'm going to get 3 times 0 plus 5 times 1, which is 5. Notice this is just A again. Okay? So the identity matrix, it's like kind of like it does nothing under the operation of multiplication. Multiplying any matrix by the identity matrix does nothing to that matrix. Here's another example with a 3 by 3 matrix. If we do this product, if I pair up this row with this column, well, notice it's just going to, we'll get the 1 times 1, negative 3 times 0, 2 times 0. It's just going to pick off that top, the 1 there. Okay, and then if I pair that first row with the second column, I get 0, negative 3, 0, so I get the negative 3. If I pair up that first column with the first row with the third column, I get 2. So notice it's staying the exact same, okay? Now if I take this second row and pair it up with all 3 columns and do the dot products, I'm going to get 5, and then 1, and then 0. Similarly, if I take the third row of the matrix on the left and pair it up with all 3 columns from the matrix on the right, I'm going to get 0, and then 1, and negative 1. Okay, so the identity is a very special matrix. It's very important, and we'll be using it a great deal. Okay, let's talk about the next definition here. The multiplicative inverse of a real number is another number such that the product always gives 1. So we have a little example here. The multiplicative inverse is 3 to the negative 1 power, or 1/3. Okay, and so of course 3 times 3 to the negative 1 just gives us 1, or 3 times 1/3 is equal to 1. So the number 1 is, this is the multiplicative identity under multiplication of real numbers. Okay, you multiply, okay, so inverses and the identity are very closely related to each other. Okay, notice if I do 1 times any number, 7, I get the number back. Okay, so the number 1 acts as the identity element under the operation of multiplication for the set of real numbers. Now, similarly though, the multiplicative inverse of a square n by n matrix is another n by n matrix such that the product equals the identity matrix. Okay? So, in other words, suppose you have a matrix A, then whatever the inverse of that matrix is, we denote it with A raised to the negative 1 power, or which we say A inverse. Whatever that matrix is, whatever that inverse matrix is, when you multiply it by A, you're going to get the identity. And it doesn't matter, notice here, it doesn't matter which side you put the inverse matrix on, which side of A. You can put A inverse on the right side of A or on the left side of A. When you do that product, you will get the identity matrix. Okay, so the identity matrix is analogous to the number 1 under multiplication of real numbers. Okay. Okay. Show that the following matrices are inverses by confirming that A times A inverse equals I and A inverse times A equals I. Okay, so let's, I did those last matrix multiplications really quickly. Maybe I'll, just for the sake of review, if that was maybe difficult for you to follow, let's do these a little more carefully. So notice I have a 2 by 2 matrix times a 2 by 2 matrix. The inner numbers match, so the product is defined, and the product will have dimensions of the outer numbers there, so the product will also be 2 by 2. This is true whenever you have square matrices. Whenever you have a long chain of products of square matrices, the result is just a square matrix of the same dimension. Okay, now let's recall how we do matrix multiplication here. To get the first element, which is in the first row and first column of the product matrix, I take the first row of the matrix on the left and the first column of the matrix on the right. And I pair up the elements. So I get 1 paired with -3, 4 paired with 1. So I'm going to get 1 times -3 plus 4 times 1. Okay. And then to get this element over here in the product, which is in the first row second column, I'm going to pair the first row with the second column, and I'm going to get 1 times -4 plus 4 times 1. Okay. This element here is in the, let's see, second row first column. So I'm going to take the second row from the matrix on the left and multiply it, do a dot product with the first column from the matrix on the right. So I'm going to have -1 paired with -3. And to that product, I add -3 times 1. Okay. And the final dot product here, I'm going to take the second row from the matrix on the left and second column from the matrix on the right. Pair everything up. I get -1 times -4 plus -3 times +1. Okay, let's simplify that. That first element simplifies to 1. This element in the top right corner simplifies to 0. The element in the bottom left corner is 3 minus 3, so 0. And the element in the bottom right corner, did I say bottom right? The element in the bottom right corner is going to be 4 minus 3, which is 1. And this is indeed the identity, the 2 by 2 identity matrix. Okay. So what we just did is we verified, I guess, this case. So we still need to verify that this case is true. So what we're doing here is just swapping the order of the matrix multiplication. Okay, I'll write this one out as well. Let's see, we're going to have -3 times 1 plus -4 times -1. Okay, and then when I do first row times second column, I'm going to get -3 times 4 plus -4 times -3. Okay, and now I'm going to take the second row from the matrix on the left, dotted with the first column of the matrix on the right, and I get 1 times 1 plus 1 times -1. And then second row and second column, I get 1 times 4 plus 1 times -3. Okay. Let's see, the first element, -3 plus 4 is 1. This next element, -12 plus 12 is 0. This element in the bottom left is 1 minus 1, that's 0. And the element in the bottom right is 4 minus 3, that's 1. And indeed, again, we do get the identity matrix. Okay, so remember, typically the order in which you multiply matrices does matter. What I'm saying is that matrix multiplication is not commutative like our normal operations of addition and multiplication of real numbers. Okay, the order of the operands of the multiplication does matter, but not when they're inverses. Okay, so this is an exception. Okay, let's get to the heart of the matter. Why do we want to be able to find the multiplicative inverse of a matrix? Well, because it allows us to solve systems of linear equations. Okay, if we can find the inverse of a matrix, we can solve a system of linear equations with it. Okay, so imagine we have a linear system, and we have a coefficient matrix. Maybe here's a simple little linear system. I'll do an example right here. So we have something like x plus 2y equals 8, and then 3x plus 4y equals 1. Okay, so here's a little linear system. Remember, we can rewrite this as a matrix equation. So here, this system is a system of two equations, plural, right? But I can change this into a single matrix equation where I take the coefficients 1, 2, 3, 4, multiply them by this column vector of the unknowns or variables, and set this equal to the column vector of containing these constants on the right hand side. Okay, so we can think of this as like A. We can call this matrix X, capital X, and this will be matrix B. So we have A times X equals B. Okay. Now, algebraically now, we can go to this point, and the idea is, well, if we multiply both sides of this equation by A inverse, if we multiply from the left, we get this next equation, right? Simple enough. And then, in going from here to here, what do? Well, notice the only difference is on the left-hand side of the equation, where we have, in the top one, in this one, we have parentheses around the AX. And then in this equation, what have we done? We've moved those parentheses around the AX to the A inverse times A. this is because there's something special about matrix multiplication, which we haven't taught you yet, but it's a simple idea, but it's has very important implications, and that is this, is that if you have A times B times C, okay, imagine three matrices all square, okay? A, B, and C are all just square matrices of the same dimension, then this is always true, okay? You can always rewrite this like this, A times B times C, okay? In other words, what the parentheses, remember, from order of operations, what they mean is do the thing in parentheses first, right? Because the parentheses from PEMDAS, P, is first. So you always got to do the operation in the parentheses first. So on the left-hand side here, I would multiply B times C, and then take that product and multiply it by A, okay? Whereas on the right-hand side of this equation, it says multiply A times B first, and then multiply by C. Okay, well, the point is it doesn't matter. You can put the parentheses, as long as they match correctly. You can group the multiplications together however you wish. It does not matter. And so often we just leave them out and we write A, B, C. So these are all equal. Okay, those three expressions are all equal for matrix multiplication. So we're using that fact to rewrite this equation with the parentheses around the AX to put the parentheses around A inverse times A. Okay, and then what did we see above? Well, A inverse times A gives us the identity matrix. And so we get this next equation here. And what's special about the identity matrix? The identity matrix times any matrix gives you that same matrix back. So I times X is just X. So here, going from this equation to the next one, we're just using a special the property of the identity matrix. Okay. Now, the key idea here is this. Now, the two yellow things, the two equations that I've highlighted. So if you have a system that you can write as a matrix equation AX equals B, then you can solve that system. If you know the inverse of A, you can solve that system by just doing A inverse times B, and that will give you X, the values for your column of unknowns. Okay, so this is really super powerful, and let's demonstrate this. Let's do the exercise here. So find the solution to the following system by writing it as a matrix equation and using the inverse matrix. Okay. So first we want to write this linear system as a matrix equation. Okay, easy enough. That means we want the matrix of coefficients. The coefficients of our variables are 1, 4, -1, and -3. And then we multiply that by a column vector of the unknowns, and this will be equal to a column vector containing the constants on the right-hand side, 2 and 1. Okay. So we do have, again, a system which I could think of as like A times X equals B. Okay? And the key idea here is we just want to skip all these steps in the middle, right? We just want to skip all these steps in the middle and go, boom, straight to there. Okay? So, but we need A inverse. Well, we haven't taught you how to compute the inverse of a matrix yet, but recall from the previous exercise that we did, this matrix here, 1, 4, -1, -3, is the matrix we're looking at, and its inverse, as we showed, is the matrix -3, -4, 1, 1. Okay, so remember that, -3, -4, 1, 1. Okay, so what we want to do is write xy is equal to the inverse matrix -3, -4, 1, 1 times the column vector B, which contains 2 and 1. Okay, so here we have x, our column vector. This is capital X. The little x in the vector is a lowercase x, okay? So capital X is the matrix or vector containing the unknowns. This will be equal to A inverse times B, okay? So I'm just using the yellow highlighted equation above, right? If AX equals B, then X equals A inverse times B. So let's compute A inverse times B by multiplying the matrices. We have a 2 by 2 times a 2 by 1. The product will be a 2 by 1 matrix, a column vector with 2 entries. The way we get the first entry is by taking the first row and dotting it with the column from B. And we get -3 times 2 is -6, plus -4 times 1 is -4, -6 plus -4 is -10. Okay, we get the second entry in our product by taking the second row of A inverse and multiplying it by the column in B. So we get 1 times 2 plus 1 times 1, which is 3. All right, and supposedly that's the solution. Let's check. Let's see, if I put those values in for x and y into the original equation, what do I get? Let's see, so 1 times -10 plus 4 times 3, that's going to be -10 plus 12. Yep, that equals 2. That checks out. Okay, let's plug these values into the second equation of our system. We have -1 times -10 minus 3 times 3. -1 times -10 is 10. 10 minus 9 is 1. Yes. Okay, so this is indeed correct. That's our solution. So if we want to write it, think of it geometrically as a coordinate pair, we can think of it as the coordinate pair -10, 3. And there's our solution set. We get a unique point where the two lines cross. Okay. Okay, so there are two common algebraic methods for finding the multiplicative inverse of a matrix A that we will present in this course. We will also look at using technology. However, other methods can be seen in a more theoretical course. Okay, so there's actually a lot of ways to compute inverse matrices, like there's Cramer's rule, there's using the adjoints method, there's several ways. Okay, but what we're going to show you is how to, oops, those should be 1, 2, and 3. We're going to show you how to augment the matrix A with the identity matrix and then use that. And I'm going to show you a formula for at least 2 by 2 matrices. You could come up with a formula for a general 3 by 3 matrix as well, but it would just be too complicated to memorize. But the good news is that the formula for the inverse of a 2 by 2 matrix is it's actually pretty simple. It's not hard to memorize at all. Okay, so let's go over this. Let's look at this. This is an important technique here. finding a multiplicative inverse by augmenting with the identity matrix. Okay, so given the matrix A, we can augment with the 2 by 2 identity matrix and perform row operations to obtain the reduced row echelon form of matrix A. Now, when the matrix A is turned into I, the augmented matrix I transforms into A inverse. Okay, that's probably a little hard to follow. So I've written a little diagram below here. So this is it. What we're going to do is you take the matrix that you want to invert, and it has to be a square matrix. You cannot invert a non-square matrix, okay? So you take that square matrix A and you augment it with a square identity matrix of the same dimension. So if A is 3 by 3, then I also has to be the 3 by 3 identity matrix. And then what we want to do is we want to do Gaussian elimination. In other words, we want to create a finite sequence of elementary row operations such that those row operations transform A into the identity. Okay? Now, we've seen in the past that this is not always possible. And so, for example, if you get a row of all zeros at the bottom of your coefficient matrix, then you will not be able to transform this left-hand matrix A into the identity matrix. Okay. The one big takeaway is that not every matrix is invertible. Okay. So what does this method do? Well, really, the reason we augment with the identity matrix is simply, think of it as it's kind of like a bookkeeping or accounting type mechanism where that identity matrix that we augment with, it just keeps track of the sequence of elementary row operations that we're going to do to A. Okay? I'm not going to go into details on that in this course. Maybe in a more advanced course you would look at that. But so that's the basic idea is you want to go from what we have, this augmented matrix on the left, to this augmented matrix on the right. And this I here should be the reduced row echelon form, of matrix A. Okay? If the reduced row echelon form of matrix A is not the identity matrix, this method will fail. You will not be able to compute the inverse. No method will be able to do it. The matrix is not invertible. Okay. So let's use this method then to find the inverse of this matrix. Let's call this matrix A. Okay, this is the matrix 1, 2, 3, 6. So let's demonstrate this method. So what we do is we start with the matrix 1, 2, 3, 6. And I augment with an identity matrix, a 2 by 2 identity matrix in this case, which has 1s down the main diagonal and 0s everywhere else. There we go. So that's I. Now I want to do a sequence of elementary row operations. Remember, the 3 elementary row operations are what? We can interchange or swap any 2 rows. We can multiply any row by a non-zero constant. And third, we can add a multiple of any row to another row. So, and the sequence is we typically want to get 1s on the diagonal to use as our pivots. And then we use those to clear things out below the diagonal. And then we use the 1s on the diagonal to clear things above the diagonal. So the first elementary row operation I want to do is to clear out that 3 right there, because I already have a 1 in the top left corner as my pivot. So what row op am I going to do? Well, I want to multiply row 1 by -3, so I'm going to do -3 times row 1, and I'm going to add that to row 2. Okay, let me write that above. -3 times row 1 is going to be -3, -6, -3, 0. I'm going to take that and add that to this row, and I'll write the result over here. The top row stays the same, 1, 2, augment column 1, 0. Now the second row changes though, and I get 0, 0, -3, 0. Okay. Now notice I don't have a row of all zeros if I think of all the entries in the augmented matrix, but I do have a row of all zeros in the A side, the coefficient matrix side of my augmented matrix. This is a problem. Okay, why? Well, because now that I have zeros there, I will never be able to transform this into the identity matrix. Okay, I don't have any element here in this position that I can use to clear out the 2 above. So this matrix is not invertible. Okay, not invertible. Okay, that happens. And we'll see a simple little formula that helps us determine when a 2 by 2 matrix is invertible in a bit here. But first, this is kind of disappointing. Our first attempt failed. So let's try another simple 2 by 2 matrix. We'll call this matrix B, and let's just keep it simple. Let's do the matrix containing 1, 2, 3, 4. I happen to know this matrix is invertible, so we won't fail on this one. So let's go through the process. First step is to augment our matrix with the identity, the 2 by 2 identity matrix. Okay. Now, recall the algorithm. The algorithm is, okay, first step, you want to create this augmented matrix. Second step, this is the long one, you need to create a finite sequence of elementary row ops to get it into this final state, where we have the identity on the left and then A inverse will be on the right. Okay, so I want to transform the left-hand side of this augmented matrix into the identity matrix. I want to do Gaussian elimination on it. So what should I do? I should clear out that 3. I'm going to do the same row op as I did above. -3 times row 1 plus row 2. And I'll write that out. So that's going to be -3, -6, -3, 0. That will get added to this row 2. And the new matrix will be 1, 2, 1, 0, 0, -2, -3, 1. Okay. Now I have a decision to make here. At this point, I've cleared everything out below the diagonal, and typically at this stage we usually make the diagonal elements all 1s. But I can actually hold off on that. When you make your diagonal elements 1s, it doesn't matter. You can save that till the very end if you like. And I think I will. Because I can use this -2, I can use this as my pivot to clear out the 2 above it by simply doing this. I can do, I'm going to take row 2 and add it into row 1. Okay. And when we do this, let's see, I'm going to be adding row 2 into row 1. So I'm going to get 1, 0, 0, negative 2 on the coefficient side. And over on the other side, I'm going to get negative 3 plus 1 is going to be negative 2. 1 plus 0 is 1. And then this row stays the same. Negative 3 and 1. All right. Just one last row op to do. Remember, I'm trying to get the left-hand side to be the identity matrix. So I need to make that negative 2 on the diagonal into a 1. So I'm going to do negative 1/2 times row 2. This will result in the top row of the augmented matrix will be 1, 0, negative 2, 1. It stays the same. Second row becomes 0, 1, 3/2, and negative 1/2. So there we go. Notice I have the identity matrix on the left now, and this will be a inverse. Or sorry, B inverse, right? We called it B. So B inverse. Okay, moving along. Here's another way to find the inverse of a matrix when you have a 2 by 2 matrix. So unfortunately, this only works in the 2 by 2 case. So the idea is, suppose we're going to just use a generic 2 by 2 matrix, and we're not going to put numbers in it. We'll just use symbols to represent the numbers. We'll use lowercase a, b, c, and d to represent the entries of matrix A. Okay, and you see the formula for the inverse of A right below there. Let me box it. So this is worth memorizing. Okay, what we have is A inverse is going to be 1 over AD minus BC. Now that's just a scalar number, okay? It's kind of a complicated expression, but it's just a number. And then we take that scalar and we scale the matrix containing row-wise D, negative B, negative C, A. Okay. Now notice, what do we have here? What happened? So notice that the A and the D were originally both on the main diagonal. But now they still are, but what? They've swapped positions. So D is in the top left, where before it was in the bottom right. They've swapped positions. And then the B and the C were on the cross diagonal, the other diagonal, and they've stayed in their original locations, but they're now negative. Okay? So that's how you remember it. You just have to remember that little denominator of the scalar out in front. You have to remember 1 over AD minus BC. And what is AD minus BC? It's you take the product of the two elements on the diagonal, A and D, and then you subtract off the product of the two elements on the cross diagonal, B and C. So it's not too hard to remember, okay? And then an interesting thing here happens, right? Notice where AD minus BC does not equal 0. If AD minus BC equals 0, then A has no inverse. Okay? So notice that's exactly what happened with the previous matrix here. This matrix A. Okay? Its A is equal to 1. Its D was equal to 6, its B was equal to 2, and its C was equal to 3. So AD minus BC, this is equal to 1 times 6, or 6 minus 2 times 3. 6 minus 6 equals 0. So as you can see from the formula, we were doomed from the start trying to compute the inverse of that matrix, because you get division by 0. It's not invertible. You can't do it. Okay. Let's see an exercise where we use this boxed formula to solve a linear system. Okay, so here's the linear system we want to solve. Find the solution to the following system by writing it as a matrix equation and using the inverse matrix. Okay, now a lot of new terminology there. Let's unpack that. So the first thing is writing it as a matrix equation. When we ask you to write something as a matrix equation, what we want you to do is take the coefficients from the linear system and create your coefficient matrix. In other words, we can transform this linear system into a matrix equation by taking the coefficients of the variables 2, 1, 5, 3, and then we multiply by the column vector containing x and y, and we set this equal to the constant column vector containing 4 and 2. Okay? Notice if you multiply out this left-hand side, you do indeed get just this expression here. Okay? Right? If you take this row containing 2 and 1, you pair it up with x and y, you get 2x plus 1y, and that has to equal 4. And then you take this second row, pair it up with the x and y, you get 5x plus 3y, and that has to equal 2. So you get the two equations from the linear system. Okay, so this is an equivalent way of writing the linear system. Now, we can think of this as, in just shorthand notation, as ax equals b. Okay? So, remember, how do I solve an ax equals b system? Well, remember, it's just like if you have something like 2x equals 6. What do you do to solve this system? You multiply both sides by 1/2, right? And you get x equals 1/2 times 6. Or x equals 3. Okay? But instead what we're going to do is we're going to do x is equal to a inverse times b, where we have capital letters. That's the only difference. And these numbers represent grids of numbers now. Or these symbols represent grids of numbers. Okay, so our x contains this x and y. These are lowercase x and y, are unknowns. And a inverse, okay, we haven't computed a inverse yet. What is a inverse? So let's use the formula in the box above. A inverse will equal 1 over AD minus BC. So remember, AD is the product of the diagonal elements. That's going to be 2 times 3, that's 6. And then minus BC, that's 1 times 5, so minus 5. So we have this scalar, and that's going to be multiplying this 2 by 2 grid of numbers. So we take the two elements on the diagonal, 2 and 3, and we swap them. So we get 3 here, 2 down here, and 1 and 5 stay where they are but become negative. All right, now, can we simplify this? Yeah. The scalar out front is just, well, 6 minus 5 is 1, so 1 over 1, that's 1. So this is just the matrix. 3, negative 1, negative 5, positive 2. Okay? So there we go. That's A inverse. And that's what we need to put right here. Okay, so we have 3, negative 1, negative 5, 2. And now we multiply by B, which is our column vector containing the constants, 4, 2. Okay, And now solving the system is equivalent to doing a matrix multiplication. How cool is that? Okay. So how do I get this product? Well, remember, we have a 2 by 2 times a 2 by 1. These numbers match. This product will be 2 by 1. The dimensions of it will be 2 by 1. We take this row, 3 and negative 1, pair it with the 4 and 2. We get 12 and negative 2, so we get 10. And then we take the second row, negative 5 times 4, that's negative 20. Negative 20 plus 2 times 2, that's 4. Negative 20 plus 4 is negative 16. And there we go. That is our solution. X equals 10 and y equals negative 16. So let's do a quick check. Let's make sure that that is correct. It's always a good idea to check your work, right? So the way I'm going to check it is by putting the values into the original equation. 2 times 10 plus 1 times negative 16. That's going to be 20 minus 16. Yep, that indeed does equal 4. That checks out. Let's plug in those values into the second equation. We're going to get 5 times 10 plus 3 times negative 16. Let's see, 5 times 10 is 50. 3 times 16, that's going to be 30. And 3 times 6 is 18, so negative 48. 50 minus 48 is 2. And yeah, that checks out as well. Okay, so yeah, we're certain we found the correct solution to the system now. The answer is, if I put it in set notation, the answer is the coordinate pair 10, negative 16. Okay. And really, this is the key idea, right? We can solve linear systems by first writing them as a matrix equation, computing the inverse of the coefficient matrix by whatever means we have available to us, and then doing this matrix multiplication. X is equal to A inverse times B. It's that simple. Okay? And the good news is, hey, the calculator can find the inverse of a matrix for us. So, hey, this is really easy. Okay. However, before I show you how to do this with a calculator, let's derive that. Let's derive the formula we just used. In other words, I want to now show you why this formula in the box at the top of the page, why that formula is, where did it come from? It's not hard to derive, okay? So remember, the starting point is what? Is this matrix here. It's just the matrix containing A, B, C, and D. And we know how to compute inverses of matrices, right? I showed you previously another method, and it's this one, finding a multiplicative inverse by augmenting with the identity matrix. So I'm going to take that generic ABCD matrix and augment it with the identity matrix, perform a finite sequence of elementary row ops, Gaussian elimination, and transform that augmented matrix so that it looks like this one with the identity on the left, and then A inverse will be on the right. So that's all. I'm going to do this algorithm. So let's do that. Okay, so I'm going to take this matrix containing A, B, C, and D and augment with a 2 by 2 identity matrix 1, 0, 0, 1, and now do a finite sequence of, I'm going to do Gaussian elimination. Okay. what I'm going to do is I want to clear out the c below the a. I want to clear out the c and make that a 0. So what can I multiply a by so that I get negative c? Well, if I multiply a by negative c over a, I will get a negative c. So we're going to do negative c over a times row 1 and add that to row 2. Okay? So negative c over a times row 1, that's going to be negative c. And then when I multiply b times negative c over a, I'm going to get negative bc over a. And then this 1 will become negative c over a. 0 will stay 0. So I'm going to take that and add it to, let me get rid of this circle. Oops. Oops. And I'm going to add it to there, that row. Okay. And what do I get? The top row stays the same. A, B, 1, 0. The bottom row changes, though, to 0. And then I have, let's see, negative BC over A plus D. Let's simplify that. Negative BC over A plus D. Well, I need a common denominator of A. So I could do, write the D as A, D over A. And then, of course, this could simplify to AD minus BC over A. So when I add the negative BC over A to the D, I'm going to get AD minus BC over A. Complicated, but not too bad. And then over here I get negative c over a plus 0. I just get negative c over a. And 0 plus 1 is 1. Okay, I'm going to erase the scratch work here. Okay, next. Well, I have a 0 below the diagonal, so now I want to start making elements on the diagonal into 1s and clearing out above the diagonal. So I think the first thing I will do is make that AD minus BC over A element into a 1. So how do I do that? I'm going to multiply row 2 by the reciprocal. So I'm going to multiply row 2 by A over AD minus BC. Okay, and what do I end up with? Top row stays the same. AB, 1, 0. Second row changes to 0, 1. And then when I multiply negative c over a times a over ad minus bc, the a's cancel. And I'm left with negative c over ad minus bc. And then that 1 times a over ad minus bc just becomes a over ad minus bc. I should probably make this a little bit bigger. Okay. Next, I'm going to use this 1 in the bottom right corner right here to clear out the b above it. So what row operation do I want to do that? I'm going to do negative b times row 2, and I'm going to add that into row 1. Okay. Let's see here. So negative b times row 2. Let me write that below. I'm going to get 0, negative b, and then I'm going to get bc over ad minus bc, and I'm going to get negative AB over AD minus BC. I'm going to add that to this row. Okay, let's make some bigger matrices so it's not so cluttered. Okay, 0 plus A is A. Negative B plus B is 0. BC over AD minus BC plus 1. Let's do some scratch work. BC over AD minus BC plus 1. Well, I need a common denominator, and that would be AD minus BC. So I can rewrite this 1 as AD minus BC over AD minus BC. And now when I add these two fractions, the BC terms will cancel, and I'll just be left with AD over AD minus BC. And that will go into this spot right here. Okay, so I get AD over AD minus BC. And then this negative AB over AD minus BC added to 0 gives me just negative AB over AD minus BC. The bottom row stays the same, 0, 1, negative C over AD minus BC, and finally A over AD minus BC. Okay, last row operation, and we'll be done. I need to make this A into a 1. To do that, I multiply row 1 by 1 over A. Okay, and I'll do that right below here. I'm going to get 1, 0. And notice when I multiply this by 1 over A, the A in the numerator will cancel, and I'll be left with D over AD minus BC. And again, the same thing, when I multiply 1 over A times this element, the A in the numerator will cancel with the A in the denominator, and I'll be left with negative B over AD minus BC. And the second row stays exactly the same, 0, 1, negative C over AD minus BC, and finally A over AD minus BC. Okay, so there is my A inverse. But of course, we can improve it by writing it as a scalar times a matrix. In other words, we can factor out that 1 over AD minus BC factor from every single entry and rewrite this as 1 over AD minus BC times the 2 by 2 matrix D, negative B, negative C, and A. Okay, and that was exactly the formula that we saw above. Okay, and this is the end of section 2.4, part 1.